You need to speak.
No, it's okay. No worries. Just put it. Yeah. Okay. No, it's okay. Don't worry. Just put it. Something. Okay. Okay, so let's start. So it's the sixth session of PMMC, Paris Mathematical Models of Consciousness, and we're very happy to have Sean Tull from Quantinuum that will be talking today about active inference. So his talk will be called, it's Active Inference in String Diagrams. So Sean, he's a researcher in applied category theory for quantum mechanics, causality, consciousness, and cognition. And he wrote also two other very influential papers on IIT, generalizing IIT, in particular in process theory. But today he will be talking about active inference. So we're very happy to have him today. And it's also the reason why it's a joint seminar with it's the second session of compositional structure and probabilistic modeling. And because I think it's an intersection between the two subject, consciousness and let's say category theory and probability, or more like topological aspects of probability theory. And so it's your turn. Thank you very much for being here.
Thanks very much. Okay, thank you. Right, thanks a lot, Gregor, for the invitation to be here to speak. And it seems like the ideal venue to talk about this work, really. So I'm very excited about that. Yes, I'm going to be talking about active inference today and how to describe it in terms of category theory, and in particular, this associated graphical language of string diagrams. I'll say everything here is joint work as well with Johannes, who's here in the room. I mean, I don't know. Yeah, don't worry. There he is. And Toby St. Clair Smythe as well, as we'll see when we get into it. And yes, as Gregor mentioned, I'm a researcher at Quantinuum. I'm in the compositional intelligence team there, which is basically a team interested in compositional approaches to artificial intelligence and intelligence in a broad sense. And compositional there means often the use of category theory and string diagrams in particular. And this work was done also as part of an FQXI project on theories of consciousness and formalizing those that Johannes was a part of as well. And that was hosted at the Topos Institute. So I'd just like to thank Topos Institute for that, and Quantinuum as well for my time on this. Great, okay. So we're talking about active inference today. We'll basically be introducing the parts of active inference we need as we go. So I won't really be assuming much knowledge of it. But just to give an idea of how we're thinking of the theory, the idea is we're thinking of active inference as a model of cognition, and it's aiming to be something very fundamental and principled that we'd like to apply to all different levels of a system, basically. So you'd like to be able to apply it both to a whole organism, as well as down to, say, like an individual neuron in that thing. And the key idea is that you're modeling any of those levels in terms of an agent coming with a generative model that it uses to relate observations it's receiving from the world to its own actions, and also some hidden states, which it's using to understand the world. So essentially what it's doing is two processes that are often called perception, where it's receiving observations and updating these hidden states to gain a picture of what's going on, and also action and action planning, where it's also taking now its understanding of what's going on in the world and using this to inform what actions to take to achieve the outcomes it wants. And the thing that's making it a coherent idea is that these are both done in essentially the same way, which is through a form of Bayesian inference. And in active inference, this is a kind of approximate Bayesian inference scheme that's carried out by minimizing a quantity called free energy. And this is often called the free energy principle. So we'll go through all of these terms in a more formal way throughout the talk. So basically, as described there, this is a very nice view of what active inference would like to be, which is a very principled theory we can apply. Ideally, you just take the generative model of a system and just apply this one conceptual system, and you get out the whole of the theory at once. I'd say at the moment it's not quite that neatly defined, so that it is useful to do more formal work on the theory. So if you actually read the literature, especially when we started this work, it's a bit more spread out, and you have to read lots of different cases. Not everything is fully just derivable in this one like ideal way that you would like. So this work was about trying to formalize the theory in a conceptually nice way to try and get to the core of what's going on. Potentially generalize it as well, and also to make it accessible. So if we can conceptualize the theory in a nice, clear way, hopefully this makes it also just quicker and easier to learn. And in particular, it's quite useful for people with a formal background to do this kind of work, hopefully, and those in AI in particular. So the main aim, though, of what we're doing here is that we want a conceptualization of active inference that just makes it simpler, basically makes it easier to learn and pick up. So that's ultimately the aim. So if you're in the active inference papers that are out there already, it's kind of suggested that an approach to doing this might be to work diagrammatically. So this comes from the fact that the generative models you see in active inference are very compositional in their nature, and they're often given as diagrams. So essentially Bayesian networks, or slightly Bayesian networks with some bells and whistles on top. So here's a kind of picture from an active inference paper. And there they essentially aim to treat the whole thing as graphically as they can, so they even have the graphical brain as the name of their paper. So if you want to do this, there is in fact a nice established formal language for doing this, where you can work with formal diagrams that also correspond actually to mathematical definitions as well. So they allow you to do the entire reasoning with your probabilities and so on that you do in a theory like active inference, just in the one diagrammatic language. So that language is category theory, and the diagrams you get with it are what are called string diagrams. So I'm going to start by introducing those, and then we'll get to how we apply them to describe all the different concepts from active inference. And the aim is basically just going to be to try and show that these diagrams are actually a very natural way to treat active inference, and even a good way to learn it in the first place. So for describing these kind of Bayesian networks and so on, in particular, there's lots of work going on in applied category theory at the moment, which is about how you treat probability theory and causal models, such as causal Bayesian networks, in terms of these string diagrams, and that's kind of what we're using in this talk. So there's a whole area of applied category theory called categorical probability theory. There's various works applying this to causality, and the way that we're going to treat generative models here is the same as in this paper with Robin and Lorenz, called causal models in string diagrams. So in this work, what we did, as I say, this is joint work with Johannes Kleiner and Toby St. Clair Smythe. And we basically took through the kind of a standard presentation of active inference, so kind of the thing you'd find in the active inference book by Friston et al., and converted this into a load of string diagrams to present the theory in these terms. And I've already mentioned this as part of an FQSI project on theories of consciousness. So here we're just treating active inference really as a theory of cognition. We're not going to talk specifically about consciousness today, but in the past we've applied these diagrams to work on other theories of consciousness like IIT. And finally, also some related work is that if you want to look this up, there's a lot of other work in applied category theory, I'd say, that's also inspired by active inference, in particular that Toby's worked on. That often goes under the name of categorical cybernetics. Okay, so I'm going to do an introduction to categories and string diagrams now to get the formal language set up. So what is a category? You can think of a category as a kind of universe of interacting processes. So it's a sort of types of systems and types of processes between them. So you could have just sets and deterministic functions between them for describing standard kind of computation, or you could be dealing with sets and probabilistic processes, or even say quantum systems and quantum processes. So the category formally consists of a load of objects. These are just labels for the systems, and what are called morphisms, or processes between them. So in the conventional notation, you write morphism F from A to B like this. In string diagrams, you draw it as a box like this instead. So we read all the diagrams in this talk from bottom to top. So the input system will be a wire at the bottom, and output will be a wire at the top, and the process is a box that connects them. So F here is a process from A to B. And what you can do with these things is plug them together to build new processes. So you can compose them in sequence. So if I have F from A to B and G from B to C, so the types in the middle line up, I can plug them together to get a process from A to C. Oh. Sorry, that was just in the wrong place there. And you can also compose these things in parallel, meaning if I take two objects, A and B, I can build a new composite system. So if A and B are thought of as systems, this new system called A tends to B, and written like this. It's sort of as just kind of those two things independently viewed as one system now. And similarly with morphisms or processes, I can compose those in parallel as well. So there's this tensor operation. So given f from A to C and B from G to D, you can build this new process f tensor G, which goes from A tensor B to C tensor D. But you don't really need to draw the tensors most of the time because in diagrams it just looks like this. You just draw the boxes alongside each other and you just think of this as two independent processes, one running from A to C and one from B to D, running along there. So using these primitive operations, you can build up many more types of diagram, as we'll see, which all describe composites. So they all result in one overall process. So if you think of the formal definition of a category, you've got to write down, you're viewing this tensor as an operation, and there's all sorts of equations that both these forms of composition satisfy. But when you turn those equations into the diagrams, they normally just become something very intuitive that's sort of a topological property of how string diagrams behave. So you would have these as equations normally, but now you can just think of them as a graphical rule. For example, if I have two boxes, F and G, it doesn't really matter where they are on the wire, it just matters how things connect up. So you can sort of slide them around on the wires like this. You can also swap wires past each other because we're in a symmetric monoidal category. And then the boxes would slide along the wires over the swaps if you look at what's going on here. Something else that's useful is just that we can have processes with no input or no output. So formally, this is because we have an object called the monoidal unit, which you just draw as an empty space. So this is denoted by I, but in pictures it just appears as nothing. But really what's going on is every object has what's called an identity morphism. So this object A, and when you compose it with any morphism, it just leaves it alone. So in pictures, you end up drawing it as just a blank wire. So if we just draw the wire A, this denotes the identity morphism on A. And this monoidal unit has that its identity is just drawn as empty space. So in particular, now, if I have a process with I as its input, you would just look like it has no input. So we give special names to some of these types of processes. So if it has no input, we call it a state, like this state row here. If it has no output, we call it an effect. And if it doesn't have an input or an output, we just call it a scalar. And these do end up being like numbers, and you can just float around in the diagrams. So the most important one is probably this notion of a state that we'll get to. So you can think of this really as like a state that our system A is in, and then we'll have processes as boxes that we plug in that transform the states. So we talked about categories in general, but in this talk, you actually only ever need to think about this one category. So all of the diagrams are really just ways of encoding operations we're doing in this category. And that's the category of positive real matrices. So what does this have? So in this category, an object is a finite set, and a morphism is a positive matrix in the way that I'll now explain. So whenever you see a wire in any diagram, it's a finite set of values of it. So you think of it as a variable, saying that it can only have finitely many values. And a box like this box M will be a positive matrix, and you could we'll write its values kind of like this. So a box from X to Y is something where given an input point in X and given an output point in Y, it gives you a positive real number, which you denote by M of Y given X like this. And then what are the composition operations? If you plug these things together, it's like doing matrix multiplication, i.e. it's like summing over the wire in the middle. So this process of M and then N, okay, it now just has type X to Z. So given X and Z, the number you get is just given by this matrix product formula. So you just sum over the Y in the middle. And the parallel, running them in parallel with the tensor operation is kind of even more immediate. You just really just multiply the scalars for each, essentially. So it's just a function that given an X, a Y, and a W and a Z does M on the bits you can, M of W given X, and N of Z given Y. So the nice thing about this is, okay, so we just described what this category is, but what it's really saying is whenever you have expressions like this, like you're doing a load of probability theory, you're working on active inference or something, you can turn expressions like these into just diagrams, right? So it's equivalent to work with this picture compared to this formula. And when they're getting complicated and there's lots of variables going on, it can end up being simpler to look at the diagrams than the whole formulae. So in particular, what are the states and effects and so on in this category? So state now on X will just be essentially a positive function on X. So this state row is just a function. Similarly, an effect would also just be a function on x. There's only one wire, so it just gives a number for each value in x. And the scalar really is just a positive real number. So what we want to do with this category is actually talk about probability theory. To do that, you just need a couple of extra gadgets in your diagrams, and then we'll be done with the setup. So what we'll have is a map for copying, and also a notion of discarding a system. And together, these mean we're working in what's called a copy-discard category, or a CD category. The copying is drawn like this. It's just a process. So every object A comes with a copying morphism that, given A, outputs 2 copies of A. And it's drawn as this white dot. And discarding takes an A and just leaves you with nothing. These satisfy some graphical rules that make sense if you think about what it would be to copy and discard things, but are not too important here. Yeah.
Just already one question. The scalar, is it something that is in the monoidal category, or is it something more?
Yeah.
You're adding something, or?
No, it is just so scalar here is just like a formal name for meaning morphism from I to I, the monoidal unit. So it's, in this category, it happens to be that it is also a scalar in a sense that we might normally think, because a morphism from I to I would be a function from a positive matrix with only one entry. So it's just it is actually just amount to a scalar, like a positive real number. So
it's just you actually use it in the particular case of n tensor n, where you could put x equals I double y, and then the scalar multiplication of the tensor product.
If you put
R and the channel.
If you put R into a diagram like this, it would amount to now scalar multiplying everything in the picture. So it does, like, if you, they kind of multiply. So if you had 2 of these together, it would be doing, if you had R and S, it will be R times S. And if you put them, let's say next to M, if you had R floating along next to it, that process would now be XY goes to R times M of Y given X. So they do just amount to multiplying everything.
And so on the discard, or the like so the relation you have after, so the ones here, for example, the left, one, like is it
So it'd be like perfectly correlated essentially. So it sends, I mean, this is what it is as a function. It's just the delta. So it's just going to force all of the A values to be the same. But if you want to think of it as a mapping on states, it's like sending A to A times A, as it were, like 2 independent copies of A for each little element, little a in A. And discard sends every element just to 1. Yeah, so for every point of A, there'd be a state that's just a point distribution on that. And then if you plug it in here, you're just going to get 2 copies of that out, because it just goes, it's just like the function A goes to A tensor, the diagonal function. And discard just sends everything to 1, so it just traces out. And so it just sums out things. Yeah. So just using these things now, you can actually define basically a large number of concepts in probability theory, and that's what's done in this area of categorical probability. So we'll just sketch a couple here. So the first is the notion of a channel. So at the moment, the morphisms are just matrices. They're not actually, but we've given this kind of probability type notation because we wrote M of Y given X. So that's suggestive. And yeah, often we are just looking at the processes which really are probability channels. And you can capture that property in diagrams. So in general, we can define a channel to be a morphism which satisfies this equation. So you'd say it preserves discarding. And in this category we care about, it does mean that F actually is a probability channel. So for each input, the scalars, so for each input X, let's say, if F was from X to Y, if you sum over Y for each X, you're going to get 1. So it sends each X to a probability distribution over the Y's. So any input here goes to an actual distribution on the output. And these are what basically all the ingredients of generative models are going to be. They're going to be probability channels. And a special case of a probability channel with no input is just a normalized state. So that's a probability distribution. So as in general, you call a state in the category normalized when this happens. And here 1 means there's just another notation for like this empty diagram. So it's the scalar, the identity scalar. So what it means is that omega, if you remember, a state was a function on X. If it has this property, it means it's actually a probability distribution. So if you sum over all the X's, you'll get 1. So the key thing is that basically probability distribution is going to look like boxes with 1 wire, and probability channels that can have input and output wires in the diagrams. And as I said, you can do lots of probability theory in terms of these components. So just another couple are marginalization. It corresponds to discarding. So that's one way to think of what it is. So if you had a normalized state like this, omega, with 2 wires, X and Y, that would be a distribution of a joint distribution of X, Y. And if we discard the Y wire, that corresponds to taking a marginal in the probability theory sense. And another useful thing is the idea of taking an expectation value. So if we had an effect E on X, that's like a function on X, and omega is a distribution on X, plugging them together gives us a number, like a scalar. And indeed, it's the expectation value of E relative to the distribution omega. So the point is that you can then take like big calculations that you would do in probability theory, like involving expectations, marginals, blah, 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 and turn them into a string diagram where it's normally, you know, simpler in some sense. Once you've learned the string diagrams, I'd claim it's simpler because you just have to write each thing and you see how the variables are being plugged together. Okay, so we'll see this more as we go on, but let's actually get towards active inference type stuff now.
So also,
oh yeah.
So the one before for probability distribution, the effect can only be in negative functions, no?
E can be it. So it's just any function on X, any positive function in this case. Yeah, I is a singleton set. Yeah.
So if you take a kernel from if the morphisms are kernels.
Well, then in this category, yeah. So in the category we're in, MATR plus, not everything is a channel, so not everything is normalized.
In matrices, yes, I understand where it's
yeah.
But
if you only had kernels, you mean like channels, then you just don't have any effects other than discarding. So that's kind of the reason to work in the broader category, as it lets you have effects, and they're quite nice. Like
that's what they do in categorical probability. They go to a bigger category where you have not just kernels, but not just probability kernels, but any kernel.
Well, I'd say the most common approach in category is to not do that and only work with categories without effects, basically, to work with categories. So a Markov category is the category they'll normally work in. That's the CD category, one of these categories, but where you say that every morphism is a channel. And then you won't have any effects. So it's kind of nice because you just know everything's a channel, so you can't draw anything that isn't normalized. But it also means you can't have like a probability as a diagram because you just have 1 as your only scalar and there aren't any effects. So here we want to like turn all the pieces inside these probability formulas into diagrams as well. So then it's kind of nice to work in the broader setting. Did that answer? Yeah. Cool. Okay, yeah, so now we want to turn to things actually relevant to active inference in particular. So we want to talk about generative models in terms of these diagrams. So these come up in active inference because the core thing is that an agent has a generative model where it will have variables corresponding to observations it receives, states of the world, and its own actions, which we'll get to later. More abstractly, this thing is normally described, well, I'll just say normally it's not simply these things, but it's quite compositionally structured, any of these generative models. So it's normally specified by various variables of these forms interacting, and it's given as a causal Bayesian network, would be perhaps the standard way, or some other type of probabilistic graphical model. So a causal Bayesian network is the form we'll consider. So this is given by projected acyclic graph and a load of conditional probability channels, where often what you really do is multiply them together and consider a joint distribution over all the variables. So here, PA is for the parents in your graph. So yeah, here's just a diagram from one of the active inference books. But what I say is that already in diagrams like this, so really if you're going to draw causal Bayesian network, you would just draw the variables and some arrows between them, and that would be your DAG. That's what you often see. But it can be very useful to instead give names to the relations between the variables, which is what they do. So they would draw diagrams like this, where they'd write A, it's capital A, for the observation. So the probability of getting this observation O2 given S2, for example, and B here. So these diagrams are already not just a graph. They're like a graph where they wanted to start putting these extra labels in. And my claim is that they're essentially converging on using string diagrams here, because these are very close to the diagram we'll end up with. So let's see how to do that. So our aim is going to be to how to describe one of these Bayesian networks just as a string diagram. So the key fact is that you can relate any one of these directed acyclic graphs to a special type of diagram called a network diagram. So can give a definition, but it's better just to see examples. But it's essentially a string diagram built from these kind of pieces. So it's got copies. It can have discards, although most of the time you don't need them. And it has boxes, and the boxes can only have one output wire, but they can have multiple inputs. And specifically, it's one with this extra property up here. And there's a known result, going back at least to Brendan Fong's master's thesis, that if you start from a directed acyclic graph, and also you pick some of the variables in your graph to be like the observed ones, and the rest would say be hidden. So there's like a subset of chosen vertices there that you consider to be the outputs. That whole thing is equivalent to one of these string diagrams called a network diagram, where now the outputs are the outputs of the diagram. So on the left, we have an example of a directed acyclic graph. It's got 4 variables, and we've decided that 2 and 3, so x2 and x3 are going to be observed.
Sorry, Sean, to
Yeah.
interrupt, but the laser pointer doesn't show up very well on camera.
Oh, okay.
Maybe you just point with your finger.
Yeah, that's fine. So here's our DAG on the left. So we've got 4 vertices, x1, x2, x3, x4, and these particular edges in the graph, which are like describing their causal relationships. And we've declared that x2 and x3 are observed with these circles. So x1 and x4 are going to be hidden variables. So that structure is just like some syntax, and it's equivalent to the syntax on the right, which is this type of string diagram. So what do? We have a wire now for each variable. So that's going to be, or for each vertex, sorry. But it's going to end up corresponding to a variable later on. So each vertex goes to a wire, and then you have a box for each wire that produces it in terms of its parents. So like, for example, x2 has x1 and x4 as its parents in the DAG. So there's a box here that produces x2 with x1 and x4 as the inputs. So then what you end up having to do is take each variable and copy it and pass it to all of these boxes where it's needed. And then we just use a system where if it's an output, so it's not a hidden variable, but an observed one, we copy it an extra time if needed, just to make sure that it ends up as an output of the diagram. The result is that we get a string diagram that conveys the same connections. The names on the boxes don't matter here. We just call them A, B, C, D. So you can look at this one and also see, okay, yeah, I can see that x1 doesn't have any parents because it just sort of appears with this state and so on. And that x2 is caused by x1 and x4. So to go now from DAGs to Bayesian networks, you have to then associate variables and probability distributions with all this data. So here we're going to do the same thing, but now in any general CD category, so any category with the structure. So we'll define a generative model to be given by one of these network diagrams, along with a representation of it, meaning for each wire in the diagram, you specify an actual object in your category. And for each box, you specify a channel in particular in your category C. So for MATLAB, and again, yeah, we use this convention I mentioned that the outputs are like observed variables and the rest are like hidden ones. So if we're in the only category that I've introduced to you here, this MATLAB plus category, this will be a causal Bayesian network because, okay, for each wire, we've specified a finite set because those are the objects in that category. And for each box, we've given, oh yeah, and for each box, we've given a probability channel of that type, right? So giving a generative model in MATLAB plus of this form would mean, you know, giving some finite sets of values that x1 and x4, x1 up to x4 can take, and distribution on A, distribution on x4, a probability channel from x1 and x4 to x2, and this other one up to x3. And then if we multiply them all, and then this overall state, you could also view as one morphism, which would be the resulting distribution over x2 and x3. But we can think of the diagram instead of just encoding the whole model in one picture.
So you can rewrite the diagram in different ways, right? Depending on the behavior you put on your variable. Like you can have the same product, same graphical model for different diagrams, depending on the order you put on your variables.
I don't think the diagrams would be, I think you'll get the same diagram. Yeah, I mean,
Start with X4.
Yeah, I don't think I mean, you might end up with a different, like, you mean choosing to draw B on the left and A on the right or whatever, but they'll be equal as diagrams in the.
Even when you have three boxes.
Yeah, if they're free, then also in the rules, then they're equivalent in the sense of if you put in the rules of, two diagrams are equivalent whenever they would always be equal up to the rules that you always have in a CD category, then they'll be the same diagram. So if you just had like two floating variables with no connections, then you just get two states and yeah, okay, up to an order on the outputs, I guess, but like for left, right order on the outputs.
You don't need to assume four rules, like identification,
Yeah, there's the rules that are always true in a CD category, yeah, like the copying and discarding rules. And some, I suppose you pick an order of the outputs, yeah, left to right, but it's like up to swapping those. Yeah. So the question then is, okay, fine. So we've turned a causal Bayesian network into this other thing. Why would I care about this other thing if it's just equivalent? And the answer is basically that because you can do probability theory with the diagrams as well, you now have just one language. So normally you have to have a directed acyclic graph. You look at that and it kind of tells you the intuitive relationships, but then you have to go to do a load of calculations in probability theory. Whereas in this approach, you can do everything in one formula and just use string diagrams for everything. The second reason is that it lets you start playing with things and tweaking them slightly. So as an example, I always said so far a diagram with no inputs because we didn't really have inputs to our models, we just had outputs. But now it's easy to generalize this definition. So we'll talk about what we call an open generative model, where we just simply drop that condition. It's now just any network diagram along with a representation in a CD category. This would be another example of a shape that an open generative model could take, where now we've allowed x2 and x3 to come in as inputs to the whole model. They don't have to have a prior distribution over them or anything like that. So this whole formal setup is the same as what's in this causal models and string diagrams paper, where it's called an open causal model instead. So there's no difference formally between these things. It's just we're going to use the term generative model here because of the intuition we have for what we're working with. So in MATLAB+, yeah, this is like a causal Bayesian network, except some of the variables just don't have a distribution over them. They're just considered inputs to the whole thing. So it's now more like describing a probability channel. So these open generative models are going to be like the basic features in our formalization. So let's just actually see some examples of them, right? So to specify one, you just give a network diagram, and then to specify like the exact thing, you'd have to say what all the channels and distributions are. So here we'll just give some sort of shapes of kinds of models you could have. So the really simplest thing, right, is you just have some hidden states S and some observations O. This is like the basic setup of how you're thinking of generative models in active inference. And that would be a generative model of this form. This would be the network diagram. So it's very simple. There's just a prior on S. So like S has no parents in the DAG, if you like, but in the network diagram, it just appears like this. There's a state on S. The sigma is the prior. And then there's a channel from S to O, which should often be called the likelihood. And that's C. So that's a network diagram. And then specifying a model of that form would just mean saying what values S and O can take and what this channel is and this distribution is. And often when you've got something like this, you're then interested in the total distribution you can get over both variables together, like the joint distribution, which here I've just denoted by M. And in diagrams that's given like this. So this would be the normal formula. Or maybe you would just, a lot of the time you just write P for everything. So you don't really give things names. You just write P. P of F O equals P of O given F times P of S. But here we're naming all the channels, so it would look like this. So this is now the joint distribution over hidden states and observations together that you get from this model. So you just stick the prior in, copy that out, and then pass it to the likelihood, get observations. Now we'll jump up to the kinds of models that you'd often see in an active inference textbook with a bit more structure in them. So we now have, as well as hidden states and observations, we also have the idea of action coming in. So this would be a model with discrete time steps. Yeah, and this is the kind you've seen lots of tutorials on active inference. So we have n time steps, S1, 1, 2 up to n here. And for each time step, we kind of have a model a bit like what we had before, in the sense that we have a space of observations, like O2 is the observations at time step 2. And we have a space of hidden states, that's like this S2 would be the hidden states at time step 2. So then we have all these observation channels from how we get from hidden states to observations, these A boxes. Yeah. Maybe I'll just not carry it. These ones. Yeah. And then what's going on? Okay, so you have the hidden state at each time step, and this is evolving from time 1 to n. That's what these channels B are doing. These are like transitions. But there's an additional variable now, which is this P at the bottom. P stands for policies, which is short for action policies. So these are the way the system is modeling its own actions now. So you can think of each policy as like a type of behavior the system can carry out. And so the model is saying, okay, at some time step, like time step 1, we have whatever the hidden state of the world is, this S1, and we have how we're acting. And those two things together are going to influence what the next hidden state is, S2. And those hidden states in turn just cause the observations. At the bottom, we just have some initial state the model starts in, and a prior over policies, which you can think of as like the habitual behaviors of the system. So they often call this the habits. So these kind of discrete time models are often used in the active inference textbook, for example. Final one I'll mention is what's called a hierarchical model. So roughly like the standard model that you'll get in active inference will be given by plugging together models a bit like the previous one, but it could now be open, so they could have some inputs as well. And then you can plug these together to make hierarchical models, as they're known. And what's nice is this really just does correspond to plugging together diagrams in the string diagrammatic sense. So let's say you have like a type of model M0 and a type M1 and type M2. You basically plug them together. So now you would like unfurl each of these boxes into its own big string diagram. And this would give you a hierarchical model. And because we read diagrams from bottom to top, it's a bit funny, but the variables at the bottom here would be normally what you think of as like the more high level variables, actually. And the ones at the top would be like the low level variables. So this would be like maybe like a slower time scale up here or something evolving over time. And at the top, you have really quick time steps in your model, or it could be that you have something high level like an object up here, and it's causing like sense impressions, and you get down to like individual like pixels or something at the top. So these hierarchical models are nice to describe in diagrams too. So we talked a lot about models, now we're just defining them. The next bit is to say what you actually do with these models in active inference. Most of it is about updating a model. So you have some idea of a model that tells you what hidden states likely to cause observations. And then you actually receive an observation, so you want to update your knowledge. Now we want to treat this categorically. So let's suppose we have like our simple form of model where we just have S hidden states and O observations. And we saw this joint distribution M over both of them before. So a model just tells us like how likely we are to see certain states alongside certain observations. If we take the prior, the marginal of that, we get our prior distribution, sigma. So this is like our beliefs about how likely each hidden state is to begin with. So it's just some distribution. Updating then is the process of, okay, you've got all this, then you receive an observation, which will in fact be given in general by distribution over O, because we're going to allow fuzzy kinds of observations. So they don't have to be an element here. They could be a distribution where you're not exactly sure what you saw. And then you want to update this prior. So how likely you think each hidden state is to some new probabilities. And there's various ways of doing that. Where this comes up in active inference is, firstly, it's like this exact form where S is hidden states and you receive an actual observation O, and that you might call perception. That's the term they'd often use for it. But another case is where you're planning actions. And in this case, the O would more likely to be some preferences you have about the future. and S would instead be our space of policies P, but we do the same process of updating. So it's like we know what we want to get in the future, and we use this to update how we are acting or what behaviors we should take. So the big part of active inference is talking about how you do this updating, how it can be done, how it should be done, and how it can be done approximately. So if you have a sharp observation, meaning you just get a point in this set O, there's basically an answer for what you would like to do in a ideal case, and that's what you would normally just call Bayesian updating or Bayesian conditioning. And you can describe this in string diagrams too, with a couple of extra gadgets. So this is O, this is the point distribution at our element O of a space of observations. If we want to update with respect to this, we do the a Bayesian conditional of our model here. So everything in this box, everything in the diagram up here is now a channel from O to S that is given the conditional probability of S given O according to our model. And the way you compute it is you can plug in this thing called a cap, which basically turns this output into an input. So it's just passing this value of O up here. And this dash blue box corresponds to normalization. So it basically amounts to looking at your function M on O in particular, and then normalizing over all the S's. I think the formula will come up here. Yeah. So this is just the normal. I mean, if there is any probability of this O happening, it's given by the standard Bayesian conditional formula then, probability of S and O divided by probability of O. Or if this O just can't happen, then the whole process is just a zero for everything, so it's not even a distribution. So this is just a way that you can describe the standard Bayesian update formula in terms of string diagrammatic components. So you use this normalization box and this cap. And we can also capture what we meant by this state being sharp. So I said it was a point distribution. You can capture which states have that property in diagrammatic terms too, in fact. So you just, in general, we can call a state in a category sharp when it has this property that if you plug it into the copy, you actually do get two copies of it. This isn't required for states in general. So in MATR+, the states with this property are actually the point distributions. So when you're updating with one of these point distributions, it will have this kind of property in terms of diagrams. And there's just an answer for what you should do is like you'd like to compute this thing. But something a bit less well known is that if you're updating with a soft observation, so like a distribution over O, and that's kind of the natural thing to treat when you're working categorically, is there's at least two sensible ways to do it. And it's just, I don't think this fact's widely known. So Bart Jacobs has written a lot about these two update procedures in papers like this one. And he calls them Jeffrey's rule for updating and Pearl's rule for updating. So in Jeffrey's rule, we kind of do something quite similar to what we saw on the last slide. We have this Bayesian conditional partial channel here, and we just plug in our fuzzy observation O at the bottom as a state. In Pearl's rule, we instead plug in O as an effect like this into M itself. So this is like taking an expectation value, if you remember in here. And then we just normalize the whole thing to make sure we did end up with a distribution at the end. These are two different ways to end up with a distribution over S. And they don't coincide in general. So they do when this O was as a point distribution, it's sharp. When it's not, they're different. So it's an interesting question, which ones are relevant to active inference. The formulas would be given by these two. And you can see from the formula as well that it amounts to how you normalize as well. So it's just where this normalization box is applied. So here it's just over S itself. Yeah, so here it's like you're taking the expectation value of O once you've already normalized for every individual possible O input here. And this one, it's just you plug it together and do one normalization. So yeah, sorry. Yeah, that's right. So I'd use a triangle notation for a point one. Yeah, and sorry, I've used like bold font O for the actual observation itself, which is a little bit hard to distinguish from the elements of O. So there's two different formulas. Anyway, there's just an interesting fact that there's two different ways of updating with respect to soft observations. The point is that either one you pick, though, is going to be hard to compute. So you can't really do these things exactly. It involves all these summations over both spaces. So what's actually done in active inference is to not do these things directly, but instead do it approximately by using this quantity known as free energy. So here I'm trying to show how you can express free energy in string diagrams, and then we'll talk about this process of minimizing it. So for that, Johannes came up with this nice graphical feature. So basically what you need to do free energy all the time is to talk about these negative logarithm functions, which you could call the surprise function. So if you've given a function on some set x, I'll do my pointing. We've got our function e on our set x, so it's mapping everything to a positive real, so it looks like a box like this in our category. And what we're often interested in instead is this function negative log of e, which you could call the surprise. So we're just going to introduce a new graphical convention for this, where we draw a green box around e. And now this we think of as like an effect, now valued admittedly in a different range here, minus infinity to infinity. But it's like the function that sends each x the negative log of e of x. And if you think about how logarithms behave, you can end up writing down some nice graphical rules these things satisfy, for example. So this is like copying is essentially multiplying when you do it with effects. So this is like the rule that log of a product becomes the sum of the logs. You can get various rules out of this thing. And using it, you can define the key concept of surprise of one distribution relative to another. So given distributions sigma and omega, we would define the surprise, this quantity s of omega sigma, like this, where you just plug omega in here. So it's the expected value of this surprise function for sigma, given the distribution omega. So it's the same as this quantity, and this is the key kind of quantity that comes up all the time in free energy expressions. And now it just amounts to, okay, green box means log of this one, and you just plug them together. And now it's a closed diagram, so it's a scalar, so it's a number. And in terms of surprise, you can define like these well-known quantities, like entropy is the self-surprise. So entropy of omega is S of omega with itself. And the key one is the KL divergence, which is a way of measuring the distance between the two distributions in some sense, which is given by the surprise minus the entropy of omega. So we can relate these expressions now to string diagrams as via this green box gadget. And from these kind of entropy type quantities, you can then define free energy. So to do that, we introduce this like general free energy quantity where we have, and then we're going to use it to pick out the two that actually come up in active inference, which are called variational free energy and expected free energy. In general, then, let's say we have a model M, like this model with hidden states S and observations O, like before. And you remember this gave us this joint distribution M over the 2. So let's say we have some other joint distribution, Q over the 2. That will normally come from some variational method. Then we just define this number called the free energy here, which is going to be by the surprise minus the entropy of Q just on S. So this Q state just on S means that we've discarded O, so marginalized out O from Q. So equivalently, it's just this diagram, this formula, this sum of diagrams, as it were. Or you could just write it, this is what it is in the standard kind of notation. Very roughly, it's a kind of measure of separation between these two distributions. And then this is a way it actually comes up in active inference. So you would normally define this quantity called variational free energy. So here we have our model M over SO. And now we're looking at a particular type of that capital Q before, where it takes this form, where we have some observation given by distribution over O like before. And we have some distribution little q over S. And now we're just putting the product of those two in onto what was the capital Q before. And this quantity is now called the variational free energy of the still order distribution Q. So the idea is we've got our model M, which is our view of states and observations. How likely each state is to lead to each observation and how likely each state is in the first place. And we receive a new observation by this bold O. And we'd like to compute this Bayesian conditional that we had before to update our beliefs about S, but it's basically hard to do. So instead, you plug in many different guesses with these little Q states, and you're finding the one that minimizes this quantity of free energy, this variational free energy. And one thing you can prove is that it has this property where it's a bound on the KL divergence between Q and this update of M given O. So in particular, it means that if you minimize this one, you can hope to reduce the difference between Q and this update that you'd like to compute. And this is essentially the approach that's taken in active inference. So you minimize this quantity to get Q to approximate these kind of updates we saw earlier. And in particular, you can think of this as like another form of updating. So we had these Pearl and Jeffrey type of updates before that were ways to get this new updated belief distribution over S. And you can think of minimizing free energy as a third one, which we just call the VFE update. So that's given our M and our observation O. This third type of update is to find the Q that minimizes this quantity. And if your O was an actual sharp one, again, you can prove that the best thing to do is to pick the actual Bayesian update. So all the updates have that property that if you have a sharp observation, they're going to coincide. Finally, I just mentioned that there's another quantity that comes up in active inference all the time, is this notion of expected free energy, which we can also define in terms of this generic free energy thing we defined. And this is always denoted with a G. So here the idea is we have our model again. And again, we have a distribution over O, but here it's going to be thought of instead as some preferences. So we have a model of hidden states and observations, and this C is thought of as like preferences for what we'd like to see in the future. That's the way it will be used. So it's defined as this free energy quantity where we take M and we plug in this new distribution on the right, where we basically say this is the Bayesian conditional from your model from O to S. And now we actually have just enforced that C is the marginal on O. So it's like saying the difference sort of between our model and this other version of a model where we actually do get our preferences. You can prove some properties this thing has. In particular, you end up showing that it's bounded by the surprise between the marginal of your model on O and these preferences, C. And in particular, it kind of approximates the surprise. That's how it's used. So it's used to give a measure of how far off your model is from these preferences, basically, this quantity, via this surprise. So it's used to approximate this quantity, which is how surprising the preferences are. So how surprising would it be if you actually got what you'd like to happen? So you'd like to minimize this to make your preferences likely to occur for your model. So we've just introduced various free energy quantities here just to show that it can also be expressed in diagrams once you bring in these log box, these green box gadgets. Now I'd like to talk about what active inference itself looks like from a structural perspective, using everything we've seen so far. So essentially, we're going to boil it down to like, well, what the conceptual ingredients of active inference are. I'd say like at a high level, this is all you really need to define it, as we'll see. So we need a generative model, and it's going to look like these discrete time models we saw earlier, but just with 2 time steps now. We just denote them by this instead of writing the time as numbers. So we've got the current time on the left here, got some hidden states that are like happening now is the idea. Observations we might be receiving now, that's O. The S and O are like the current time. And then S dash and F are future time. S dash are some future states, and F are possible future observations we might get. And again, we have our own actions appearing at the bottom here via these policies. So this is saying, you know, whatever the state of the world is here and how I'm acting are together going to determine S prime. I haven't put labels on these boxes because it just doesn't matter, but you know, you could just give them names. The one that matters is that we'll use again is this E. And that's our prior over policies that we think of as the habits. So this is the way the system tends to act. So it's telling you how likely it is to follow a given course of behavior. So this is all you need a model with this structure to start applying what they do in active inference. And what active inference consists of is now you're given an observation in the current time. So that's this distribution O. And now you're also given a distribution over the future time, which we think of as the preferences. This is like what we'd like to see in the future. And active inference is the process then of planning how we should act, which amounts to a kind of updating of our policies. So given this O and C, we're going to do a kind of update process like before to update our habits to get a new distribution over policies that we can call like our plan, because it's telling us how likely it is that we should do this or that. You know, if there was just one course of action that was going to work, this would just be like a point distribution on that one policy. So the way to think of it is that it's taking, you know, we basically want to make the plan be such that we will get our preferences, but we have to take into account like what we're actually seeing about the world when we do so. So that's where this observation comes in. So if you look in the active inference textbooks, you'll find like a formula for how they should do this, which they essentially relate to the free energy principle, and they give various justifications for where this formula comes from. So it's a formula. Pi is like an individual policy, like an element of P. So it could just be a little p, it just looks like a probability, so they use pi. And they get this formula, you know, that involves the habits, the variation of free energy, and the expected free energy that we met earlier. But basically, it's kind of hard to see where this formula actually comes from. But they give a justification for it, which kind of amounts to treating this EFE like a prior, but it's not really a prior because you have to actually even kind of compute this thing before you even get to this one. So it's a bit hard to see where it comes from. So what we want to do is sort of understand how this formula might drop out from the structure of this kind of model that we're even looking at. So we did a sort of graphical derivation where we start from the string diagram for the model, and just think about what these quantities are and like end up with this formula to get it in a more conceptual way. So I'm going to try and sketch how we do that now. So if we think about what we said active inference was, this is what we'd really like to do. So sorry about all the letters, but remember, so O is like the current time. This is our current observation. F is the future. So this is just our preferences. This C is the preferences for what they'd like, what we'd like to see in the future. Our model is giving us this distribution over policies and these two things, which I've just called M. And what we'd like to do is a kind of updating of our model using these two. So in this picture, we're doing the Pearl style updating. So you plug them in and normalize. So this is like an ideal kind of soft Bayesian updating of our model with respect to O and C. And the result would be a new distribution over policies that would tell us, okay, if you want to get these preferences, and we know that this is what's going on at the moment, then these are the behaviors you should carry out. So that's what we'd like to get. And we're going to see how this expression on the right relates to that formula that we had earlier. So let's just take the bit on the right. This is this M. This is our model with the observation and preferences plugged in. Now, okay, so because of the structure of our model, we know that M itself, this distribution, takes a particular form that looks like this. It doesn't matter that much. It's just saying, you know, there's a part related to the current time, S and O, and these are causing the future time, 1 F. So there's some ways to fill in these boxes. I've just called them both M. So you can prove, maybe I'll just make it explicit what I'm saying. Because the model takes this form, we know that we can rewrite this like this. So there's the causation just goes from S, the current time, into the future ones, like not the other way, for example. So it'd be possible to write M for some channel here and some channel here. I've just called them both M, and we'll just distinguish them by their types. And then we're plugging O and C on top, like before. And at the bottom here, we have our habits over policies, P. So this is our likely, what's the behavior? So what you do in active inference, okay, you start by focusing, let's just look at this part. We'll focus on this part that just relates to hidden states and observations in the current time step. And we will start by approximating this part. And you can, this step is often called perception. So what you do is essentially this VFE minimization we talked about before, but now we're doing it for every policy because there's this P wire coming in as like an input. So for every policy, you carry out this whole process of, you know, if you plug that policy in, you'd now have a joint distribution over SO, and you try and compute this Q that we had before that was the VFE update. you're approximately updating M given this observation O for every policy. So for every policy, you minimize VFE, you get this box Q, and you can prove that it will have this property that what's in this box here in blue will be approximately equal to this now. So policy goes in and is sent via Q to a new distribution over S for each P. So for each policy, you get your new updated beliefs about the hidden states. And you have to multiply this by this quantity e to the minus of the VFE. Okay, that's the perception step in active inference. Up here now we have, is that all right? Yeah, we now have something involving the future time instead, right? So if we have a mapping from policies to distribution over S and then up to the future time, so just collapse that together. So these two bits will collapse together. Let's call that MQ. So this is now a channel from policies to future states or future observations, however we think of this F. And we now need to approximate what's in this blue box. So this is just plugging our preferences in. So it's essentially saying how likely our preferences are or how surprising they are. This is done with this expected free energy quantity. So for each policy, again, you calculate this expected free energy, and we denote that by G of pi. And you can show that this will be approximately equal to, for each pi, working out e to the minus of your expected free energy. So these are just basically, you use these two approximation properties for free energy to rewrite those chunks of the diagram. And now we have an expression, I'll just stop here, looking like this, right? So we have something over P, like a state of P. So this is close to a distribution. And it just involves the habits, E, and these two free energy quantities. And we were supposed to do this normalization step at the beginning of the updating. I just didn't draw it around every picture. So if we now draw a normalization around that, you'd end up with this. And this is just another way of writing the same formula here. So we've arrived at their formula because what we've got is two exponentials in here, e to the minus f, e to the minus g. And then we normalize, and that ends up as this being the same as doing this softmax here and sticking the log in front of this. So this is another way of saying the same thing. So for each policy pi, you get this distribution described by this formula over how likely they all are. So basically gone from the structure of the diagram and a couple of graphical rules that give you approximation properties for each of these free energies, the F and the G. And we've used those, and then we've ended up with this formula. So it'd be nice to make this like more precise still, like to see sort of to quantify these kind of approximation steps we made and things like that. But at least it's a way to see how to go from just the structure of the model and actually end up with this formula. And our claim is this is the nicest way to get to the formula that's out there compared to what's normally done in the literature where it feels a bit more ad hoc.
How did you get the exponential minus G?
It's just in this step basically. So it's just a general rule that basically if you want to plugging an effect onto a state. Yeah.
The F is for the variational inference.
Yeah.
Like approximation and the prior.
Yeah, for each policy.
Just preferences. Okay.
Yeah.
And how do you, so you presented basically this for one step forward in time.
Yeah.
And the inference part is on all the steps up to now. And the preferences, so how do you include it in?
Oh, it's a good question. Yeah, I didn't really say what like each time step was here, right? So we treated it like it was just now and future here, right? And then really you'd probably have one of these discrete time models earlier where there's n time steps, and you would have, say, like the first little n are considered to be now, like everything up to now is now. And then the future is like everything up to some huge time step in the future, say. So yeah, I'll just say that. And then sorry, what's your question at that point?
No, so you're saying that the diagram that you showed with S and S prime for now and the future, the S could be in fact a lot of in itself already. Yeah. A Markov chain.
Yeah.
And with the P and P with the previous observations and previous states.
Yeah, normally S itself would just be, it doesn't have to, it wouldn't be PMDP, it would just be the product
mean,
of,
SNO.
it would be like,
SN. I mean, like in the diagram, what
Yeah.
you're saying is that the SNO, yeah, exactly, could be O is a collection of observation until time big T, and S collection of state until time big T. And so
Yeah.
S prime is T plus one, for example. So this kind of
Yeah, it can be that. Yeah. I mean, I think that normally S itself is like a product really of like n many, and there's like n many of these boxes of how to go from each S to the observations. And that's just what this is equal to, and what this is equal to.
So there's
And this could also be many, or it could be one more time step, or
there's
Yeah.
also something that I don't know if you can, probably you can, but so something that I found puzzling with respect to acquisitions the first time is that you need to approximate your, like when you do the variational inference, what you are inferring, if you do naive bias, you have a product of distributions. And these are the distributions that we will use to plan what will happen in the future. And so you're gonna have a term with respect to preferences that can be a sum of term in distant futures. So it can be what will happen in time t, t plus one, t plus one, t plus two, t plus three, t plus four. And to do this,
Yeah.
you need to have a way to extend your a posteriori to what you think it could be in the future. So what I mean is that when you do variational inference, you basically compute the posterior with respect to observation up to now. But to be able to do the second phase with respect to the exponential minus g, then you need to be able to say, what is my distribution for the future states?
Yeah, so you mean just for this G part, do you agree? It's just that part we're talking about.
Yes.
So
my question is,
yeah, I think
what happens if in this G, you consider sums of what will happen at time now and time after, but the now can be any time in the future. This happens sometimes you see it in the formulation of active inference. That they have a sum.
I was normally thinking of it that the now is, so this SY before, let's say the now is everything up to like our actual time now. And this F would be lots of time steps, like the next time and the load, and like 100 more or something. That's like as far into the future as I'm willing to look that I can compute. So the many steps would be in both, but in particular this F would also be many. And you would, so you do need to be able to have like preferences for like all of those time steps, and you do have to be able to compute like a distribution over all of those future time steps in this approach, I think. But I don't know if we covered it, and maybe we need to go on the board for that.
Yeah,
to do it.
I
Were you thinking that do you think you need something more than you actually have here formally to do what you?
No, but I think it's hidden inside of what is.
Yeah. MQ, yeah. So Q is like, yeah, you go from your observation basically to get your new updated beliefs about the hidden states. And here it would be for all time steps up to now, in theory. I mean, you do it just for one or whatever. But yeah, this would be all time steps up to now. And then you have your model already includes like a forward channel for how to go from now to like 100 time steps in the future, let's say, where you just keep predicting. So this M would let you get all these future observations.
Maybe we can go to the blackboard. But what happens is that imagine that C is in fact the tensor product of C for all the futures that we can have.
Yeah.
Distribution. And then you don't have exactly that N, that the exponent, that the G part, so the Kullback divergence, with respect to the each individual preferences at time t, can be written as a sum of preferences with respect to the marginal at time t of n. What happens if you do C, which is C tensor product, all what happens after, and you apply your model, like you apply your MC, and then you compute the exponential minus G.
Yeah.
G cannot. I don't think it can be decomposed into a sum.
No, probably not, right?
Yeah.
Only they'd have to be independent, I think. And they won't be here because they'll be, yeah.
And this is what does it. Well, this is what happens when you do variational inference. And you assume that the variables are independent, then you have this.
Oh, right, yeah.
But I think probably.
But it's quite weird to assume. I can't remember where it was, but I feel like we saw point to Johannes where they were doing this thing of you need to assume variables are independent to apply some of the methods, but then they were literally applying them to like S1 up to Sn or whatever.
Yeah.
And these are things that shouldn't be independent because they're like the thing as it evolves over time. It's very weird
But
to
they
use.
assume this is, but I think what you're presenting is in fact more captures all the different settings. But yeah, because I think they assume that you have different distribution in the future, but that they're independent. So that they try to fit independent like this variables that are in the past, fit them as independent variables, but not identically distributed.
Right.
And then they just, if I remember well, what happens is that you take the distribution at time t, propagate it at time t plus 1, and you do this as if you were every time in the future starting at time t with the prior you had at time t, with the but the distribution you have at time tau is the last one that you have with respect to observations, and then you propagate it one step further, even if this implies that you're looking several steps away in the future.
Mm.
And this is in one of the diagrams you showed at the beginning, I think. Right? I mean, the idea that the distribution at the future time is just like generated from the last one by application of what I think usually is the D operator.
What the operator?
So I think like the way they represent
I think, yeah, I can go back to that.
Which basically,
Yeah, exactly. Okay, I see.
yeah. And that's like, I think it was.
Oh, is that all you? Yeah, but I thought you were saying they were doing something weirder than that. I mean, that's what I would have thought you do. You just propagate one time step at a time. That's what we're saying there. But you're saying they do it in a.
You can. I think this way is the most general. Is the one that which is natural. Then it can reduce to the case where when you assume that the variation in the Q gives you IID distributions on your states, and then you can say that it's the same thing. Then looking what happens one step. Like what happens one step after, and you sum on all the possible futures. But the more general function normally should not allow you to cut it into several.
Yeah, I don't think the general G wouldn't have this sum property, and you're saying they normally make assumptions that it will do that in some way to make it feasible.
I think
like,
maybe there's this. I don't remember well, but I think that if when Q is assumed to be IID, it gives you this, but when Q is not IID, maybe some people still use the same function, but they should be using an approximation of this, but then there's maybe no way of approximation. But okay, no, just
well, I mean, I agree. I don't expect every case that active inference is used to actually fit this formula anyway, because I think it's always tweaked in different settings, isn't it? Ideally, it would be like a special case of this where you just make like an assumption about C or something, because at least then it would connect with their formula that they say. Yeah. Okay. And then just the last thing is this so we talked about at the beginning, I had the statement that the aim of free energy would be something that you can apply to all levels of a system. So it should be that we think of like the agent as a whole as doing this kind of minimizing free energy, but also like the individual subparts of their model, or even like neurons in the brain or something, are all doing a form of active inference. So if you'd like to have that, you need to prove some property that minimizing free energy at different levels relates to each other, so that a system can say you'd like to say it's minimizing free energy globally, like at a high level, and then it's doing it by minimizing free energy locally in these pieces. So this is a kind of compositionality property of free energy, and we wanted to see if we can actually like prove some property like this, especially because the categorical language is very nice for talking about compositionality. So to do that, we need to make the definition of free energy that we had earlier a little bit more compositional, which means basically allowing it with more inputs in things. So I'll start by just bringing back VFE, the variation of free energy, and remember we had our model M with this joint distribution, an observation O, and then the VFE was a property of this belief distribution Q, given by this formula on the right. So what we want to do is generalize this to a version where our model M can now have inputs coming in. So these inputs are called I. And this isn't the monoidal unit, it's just a variable called I here for I for input. So M is now more like an open model, it would be the idea. So I has some inputs, it has some outputs O, and we're looking at the overall channel where we also look inside and we look at these hidden states S going on in there. So now we need to generalize. Okay, we still have an observation over O, and we're generalizing our Q. Now, instead of just being a distribution on S, it's going to also be a distribution on inputs. And we'll use that fact to allow us to get just one number out. So we'd still like to go from one of these open models, which has many inputs, but just get a single number quantifying its free energy. So we've tried defining out this new quantity called the open VFE. And we use this formula on the right for it, which is basically a tweak of the normal VFE formula to now plug together to make a scalar from this new data here. So our distribution Q now is a distribution over inputs and hidden states, and maybe that, set of factors in terms of a prior over inputs and some channel relating each to S. But whatever it is, we plug it in down here, and we similarly have the same graphical property of applying log boxes and getting the entropy here. This part's the same. We have the entropy of Q. And what we do now is take our model, and rather than treating it just an effect like we did before, we only take the S and the O out of the diagram, and the I remains as an input. This is a way to make a new kind of free energy type quantity. And this is the part that's most open kind of about the work, I'd say, is working out how this is definitely the right way to define free energy for a kind of open model like this. But what we have found is if you do take this definition of a free energy for an open model now, you can prove that it does have some compositionality properties you'd like. So there's two results proving that this open VFE quantity is compositional in two senses. So firstly, if you just have two models in parallel, then you want to compute the free energy of those, then you just do it by summing over both of them. So this one's like the most trivial one. So this is just saying we have two models of this kind of form, M1 and M2, and so they have their own independent, I1, S1, O1, and I2, S2, O2. So we just have our Q happens to just be given by two separate belief distributions, Q1 and Q2. Now we just have two independent observations, O1 and O2. So it's just like having two models in parallel. So it really should be the case that you can just compute it by summing the two. And indeed, it does have that property. More interestingly is this property to do with sequential composition now. So this is if you had a model M1 that goes from some inputs, and it has outputs O1, and these themselves happen to be the inputs of another model M2, so you're plugging them together. And this is the kind of picture that you get all the time in these hierarchical models, where you'd have, like I showed the picture ages ago, these M's stacked together. So you'd have two models that can be plugged together in sequence, as it were. Now the only output of the whole thing is just as observations at the top. So the observations are only over O2, but your beliefs are over I1, S1, and I2, S2. Then again, you can prove you get this summation property in a certain sense. So let me just see if we get this right. So it's basically given by summing over the free energy for each model individually, for M1 and for M2. So for M2, you can just use, the beliefs about inputs 2 and your observation. For M1, it's more interesting. You don't have an observation, right? There wasn't an observation on the left here. But instead, you get it by passing down the beliefs Q2. So you just take the marginal of those, because we had that the outputs of this model coincided with the inputs of the one above. The way to think of it kind of is that you have these two in sequence, and then you would do something like the later model would do its own minimizing of this free energy quantity to get its Q, and then that Q is now passed back down to M1 as an observation, and then M1 can do its own free energy minimization. And this is kind of the way they talk about processing in these hierarchical models, I would say. And this result says, okay, if you define this new version of free energy that's for open models like this, then it indeed has this summation property. So if you take these two properties together, it's saying if you had a big hierarchical model built out of all of these, you can say the whole thing minimizes its overall open VFE by minimizing the open VFE of each of the individual pieces and just summing them together. So it's enough for each part to locally think about minimizing this quantity. Yeah, so, okay. Yeah. Do you want to talk about this part?
I just want to say I really like this part specifically because like so it shows that the brain doesn't have to like low range minimization, but it can do it locally. And I really thought that really nice. And I think it was known a little bit already in like the context of this Laplace assumption, Laplace approximation, but yeah.
Yeah.
I just want to say I'm really happy about.
Yeah, I mean, I think this sort of property is what they would, whenever you put forward like a free energy type quantity, it kind of should have this property basically, or that's what they want to be true. That's how they talk about it. And it's nice to be able to actually prove it. Yeah. Okay. So just to wrap up, basically the aim was to show that you can use this string diagrammatic language to describe active inference, and the claim is that, you know, once you pick them up, they're a very natural way to do so, and that's because you can describe both the structure of the models in an intuitive way as a diagram, and you can do all the probability theory with the diagrams. So you can describe everything you do in a framework like active inference, just using this one formalism, and it has these intuitive and formal aspects together. In particular, we saw how to describe generative models, free energy, and the updating procedures, as well as like active inference itself, all in terms of diagrams. There's obviously loads more you could do here. You could keep just taking work on active inference and translating it. More interestingly, there's various directions listed here. So this quantity of open free energy we put at the end is the most like speculative part, because it wasn't taken from adapting any of the existing active inference stuff. It was a new definition. So it'd be really interesting to get feedback on what people think of this definition of this open BFE. Throughout the talk, I just said, okay, you minimize free energy all the time. Like I just said, you get this Q by minimizing it. And I didn't say how you do that. So that in practice is done by all these algorithms, like message passing algorithms. So I think many people would think to really capture all of active inference, you should have those treated diagrammatically as well. So that'd be nice to do. There's lots of questions about these different forms of updating we met. So we said that for soft distributions, there's at least like these two sensible ways to update that were called Pearl and Jeffrey. And then we said that minimizing variation of free energy is kind of a third way that you can update, and that's one way to think of it. So just thinking about how those all relate to each other in the context of cognition is quite interesting. I know Bart Jacobs is interested in that as well also, and just put out a paper like last week or something as well, continuing these kind of thoughts where he does include VFE updating as well alongside these. And in particular, yeah, it's interesting that the way we did the active inference derivation was just in terms of this Pearl updating. But the Jeffrey updating is more the way the active inference people actually speak. Normally, they think of it like computing Bayesian conditional channels. It's the way they talk about it. So it's just interesting that actually the Pearl one was the one we were able to connect. And then there's connections to all sorts of other work. So actual approaches to category theory for AI, like this compositional intelligence work we're doing at Quantinuum I mentioned, as well as all the other stuff going on in applied category theory under this name of categorical cybernetics. And then we didn't talk about consciousness today, so the hope was to then use this work at some point to spell out the different ways that consciousness has been formalized in active inference, now using this language as the formal language for doing so. So we still hope to do that at some point in the future, I think. It'd be nice. Yeah, that's me. Thank you.
Okay, so let's discuss for the students among us, the students, Milk and Songrin, do you have any questions? I don't have to be smart, and they can be just, oh, I did not understand that part. You know, explain it. So,
Yeah.
In your opinion, what the benefits to cut your mathematical equations into your string diagram?
Yeah, I'd say, yeah, the main benefit, I mean, once obviously with any language, there's a process of learning it, so it might not seem simple at the beginning. But I think the fact that like when you're dealing with something like a generative model, something structured, you end up drawing diagrams in some form. Basically, it's just more natural to draw either a directed acyclic graph or like the kind of diagrams you see in the active inference books. So you'll end up with a diagram, and then you'll end up writing a load of probability equations. And you want to kind of think about how they relate to each other, and you might refer back to the diagram a lot. But if you use the string diagrams, you can just have the diagram as your language where you do the probability theory as well. So it's just like having one core language that you use for everything. I think makes it more intuitive. Like if you want to reason about the probabilities, but you're taking into account the structure of the model, it's like just more immediate to do it with the diagrams. Somewhere where it came up similarly was in physics when they were first invented, was like basically by Roger Penrose, who was doing all these calculations of tensors in physics, and then he just found he wanted to turn them into the diagrams. And it's kind of the same thing where the formula just, the connectivity rules in the formulae just are more naturally expressed by plugging things together. So that's the main benefit. And then on top of that, you can say, okay, now I'm in a category. I can sort of generalize things and change what category I'm in and immediately generalize the model as well. But I think the most important benefit is just as a tool to make it easier, basically. Yeah.
Just a
Yeah.
follow-up question, a bit naive. Can you use this approach also to try to explore optimization of algorithmic solutions to actually implement things? Can it be useful for, you know, because often so those model variability run in particular, so they are complicated when one of the simulation heavy, and can it be used as a way to explore?
Would you not need
Because it
to?
looks like electronic diagram to some extent, and I believe that you guys at Quantinuum use this type of formalism in the context of quantum computing, or maybe?
Yeah, it's certainly.
So is that also a cue about, does that give you cues or direction about how you could actually compute those things?
No, it's a good question. It's quite broad, I guess.
Yeah.
In quantum computing, we use them, to describe quantum circuits or something. So you'd have a diagram that actually shows what the circuit is that's being run on a quantum computer. And then you also might translate it to like a more low-level thing, like this graphical system called the ZX calculus, that lets you then rewrite it and make it even like simplify your circuit for you. So I guess it's sort of whether there are similar graphical tools here that would speed up, I don't know, let you see what you need to compute and then like make it more efficient, I guess would be the closest thing. Other than that, I think it would require answering the second question, I guess. I suppose the algorithm, the side you're talking about is closer to message passing algorithms and stuff, whereas this is like a sort of conceptual level, but it doesn't tell you like the best way to compute something. You can't really see from the diagram itself that like free energy is easier to compute than just doing it directly or something like that. It's just a structural system. But
I guess you guys have seen the recent, now it's not that recent, but quantum formulation of active inference, right? That's, now the group of Carl, Kristen, Open Publishing, they will present.
I think I'd like to know more about that, to be honest.
The kind of classical form and quantum.
Yeah.
Since I know you guys use that for quantum computation, I was wondering whether the quantum formulation of the free energy principle and active inference then it could make maybe some interesting offer some interesting directions perhaps to
you're right.
implement it in a quantum computer. Sorry, it's very speculative.
No, that's great. That should be another point here, I think. Yeah, that's very good. I need to read that stuff basically, because you would hope that we can, it'd be interesting to do similarly to what we did with IIT, basically, where you see how close this quantum version of it corresponds to something like this, but where you change the category. You couldn't just take this work and just change the category to a quantum one here, because we used copying everywhere, and copying is the thing you can't really do in a quantum setting. So I'm kind of curious to see what they do actually. I'm not really familiar with what they've done there, but since I think it was I've heard. I think I need to look at like a lot of what Chris Fields has done. Is the impression I'm getting. Yeah.
I had a question with respect to the first dance, your answer to your first question.
The
thing is, when it's problematic is the log, right, with your box diagram.
Problematic for what, sorry?
For applying it to other categories that have copy operation, that are taking the log.
Well, I'd say the copy itself is a problem, right? And like
The copy itself is the problem.
Well, like to do, you don't have a copying morphism like that in the category of quantum processes.
But if you
So
have a diagonal,
you could pick one for every system or something, but it's like a bit ad hoc. It's a bit, you're not necessarily.
but the mean is just, for example, very like just going from the discrete spaces
Yeah,
to continuous spaces.
yeah.
When taking the log is very problematic.
Okay, yeah, I can believe that also, yeah. I hadn't even got that far, but so I already had issues with the copy, but yeah, I agree the log is also
So did you think
tough.
about how to characterize the log? Or how to
Uh,
make it the more like
yeah. Yeah, it's a nice idea. No, it's
The
really,
question is how to define it.
yeah, yeah.
To other
I don't know if we have-
understanding in which all the rest would fall.
Yeah, that's a really nice idea. I guess you'd like to relate it to like von Neumann entropy or something in the quantum case.
Or
Because there are notions of entropy there. All we have is like abstractly is more than these, but like, we have that it's like an operator on your category and it satisfies various graphical rules, like including these and some more that we list. And that's all we use from it to do to prove this theorem at the end, right? I mean, maybe they didn't make that clear. Oh, it's going to be ages, but the compositionality theorem at the end, we just use the graphical properties of it. We don't actually have to like write log or anything. So, so that's kind of a nice part of it as well. So in a way, we've reduced it to just those properties. So I suppose you could say that, yeah, if you had something like that in a quantum setting, this would give you a form of free energy there.
so you have a proof that is purely, let's say, graphical.
Both of these
The
results,
second, okay.
yeah, they're just graphical. They're just properties of the box. Because I mean, it's not too many steps actually to go. I mean, you have it in terms of log boxes up there, and these are just like statements about things in parallel or things passing through. Yeah. But yeah, even the properties themselves refer to copying, for example, like one of the log rules. So it is a bit
Yes.
so it is a bit funny in the quantum context. Like you probably want some other way to capture like von Neumann entropy or whatever. So it doesn't seem like it will work out super neatly. But then end up, they've said something, I guess, in this Chris Field's work and stuff. So I need to see how they treat entropy there, really. So they have a quantum free energy quantity, I guess.
So the sum would make sense in a copy discard category. Like I mean, like if you want to define the box, the green box with these properties,
Yeah.
the sum, what would be the sum?
Oh, I see. Yeah, I mean, the sum doesn't really live in the category either. In the sense, what the box actually does is take it out the category into like formulae with values in, or like functions with values in this set minus infinity to infinity, where you actually include infinity as well. So I feel like you could do the same thing maybe in the quantum setting. It would be, yeah. So you could have sums in the same way, I think, because you're kind of leaving the category. Like if you're going from quantum processes to just entropy and it's just a number, then you kind of left. So I think that bit would be the same. So the sum would just be summation in this. So it would again take an effect in the quantum setting now to like probably just a function on the Hilbert space that sends each to a number. I mean, it's quite speculative. I don't really know about this. I just don't.
Setting, because this is basically it turns the log turns product into sum. It's seeing like distributions, seeing them as Hamiltonians. So as energy, and therefore like this duality, it doesn't. I mean, like this is like Hamiltonians are operator like observables, and the distribution states. In the classical setting, in the probabilistic setting, the log you cannot. But maybe I mean I know that there are things graphical. I think I saw this graphical models for quantum systems. So and there's some work on the propagation for these systems also. So probably there must be this. But I mean like the box is the classical setting is relating a distribution when you take the log to a Hamiltonian. And so probability distribution, u exponential minus h equals p up to normalization. So when you take the log, basically you're sending a distribution to Hamiltonian. Okay, up to you can do a multiplicative value, but it becomes a scale up to a scalar value. But this going from one to the other changes the perspective on the distribution you're studying.
Yeah.
And I think this is it's a little that could be generalized.
So probably have to look at how people treat Hamiltonians, how that relates to quantum diagrammatic stuff, basically, because there is some work in quantum chemistry and using ZX there where they really work with Hamiltonians, but I don't know it in detail. Because if that's what it's about, then that's probably the closest thing that you can do with quantum that's known at the moment, like diagrammatically, is that picture of going from something to its associated Hamiltonian, I think. Yeah, it's in a really nice direction to work out, though. I mean, do you feel like, do people take the quantum active inference seriously as like a proposal, or like, where is it, how is it meant to be used anyway? Is it meant to just say, is it because they want active inference, like theory of everything?
I think there's more ontological idea that any system has a Markov blanket and some doing active inference in that context. If the quantifier is any, I want to know how it's going to quantify.
Yeah.
They identify in the quantum setting and toric phase field, and probably they will say something wrong, but at least for reading some of those papers and trying to understand the Markov blanket is identified with the concept of holographic string in quantum mechanics, with reading and writing operation. Of course, I'm incapable of assessing it. And I guess it's part of the difficulty, the reach of this theory, to understand it very deeply, precisely. It's a very small audience.
Yeah.
So among everybody in the world, somebody like you probably would be in a position, given your work at Quantinuum and what you do here, in better position to really precisely assess. So
yeah, I do feel like I need to read this stuff. Yeah.
yeah, but I think it's serious and interesting. It doesn't,
yeah.
It's quite a big head mind.
Yeah.
But I can, sometimes to me, it seems to go to broad direction, like the theory of everything, but this notion that maybe even, proton can be modeled as something that performs the form of inference.
Yeah.
In the sense of active inference. And so perhaps there is a kind of already at a minimal level, a form of observer that's intrinsically exists in the very fabric of the quantum world. But I'm probably already saying things that are not correct, but that's, I guess, what you feeling you get from the big picture. But Greg, did you read some of the paper on precisely? No. I forwarded some to you, but you did not have time to.
So I remember, so you forwarded and read it, but not in detail.
No. But you'll find plenty.
Yeah. No, yeah, I've got the impression. Yeah.
And I'm sure directly once you have.
Yeah, there's a lot of over there. Have you read any? Anything we should do? Yeah, it would be a nice direction to take, definitely.
Should we conclude for today? Do you have anything you want to have? We'll have you.
Oh, yeah, did you?
We'll have you tomorrow.
Did you want to say any more
Yes.
about this work anyway, Johannes?
No,
It's
just
your
so
work
that-
too.
Yeah, so maybe like just one thing.
Yeah.
I mean, we can discuss about the relation to consciousness, between predictive processing, consciousness, data. I think there's suggested stuff. But like what wasn't so apparent to me when we did that work was that it could be really handy for exactly computational phenomenology, like in the normal sense of relating integrated processing. And I think I'll say a little bit about that tomorrow too. But yeah, so that's like in retrospect, I think. So it might not be like, I mean, so I think the reason we did it was really because what we had in mind was actually part of a bigger project where we wanted to just formalize some of these proposals of how predictive processing relates to consciousness, some of which are very concrete, but others are also more on the methodological side. And yeah, and then that just took so long to do.
Yeah.
Pactographs and whatnot that we didn't get to that yet. But now I'm thinking, like, generally, I'm super interested in the relation between these concrete proposals of how consciousness relates to predictive processing on the one hand and computational phenomenology on the other hand. And there has to be, of course, like a relation between consciousness and phenomenology, or the consciousness maker, maybe. And so. But that's why I was really happy, like, in retrospect, and that's also why I caught my talk so weirdly.
Looking forward to it.
Yeah.
That's the kind of point that you raise in issues, goal that we should pursue is what we have been trying to do from the outset in modestly, in limited manner with this projective consciousness model.
Yeah.
Connecting somewhat phenomenology to functional, at least understanding in what sense phenomenology may actually reflect something functional in the context, for instance, of activity. But that's for another discussion.
Yeah.
Okay, so should we say goodbye to the web and do something else? Well, goodbye, everybody. Thank you.
Bye.